be up there. Okay, yeah. You guys need, if you need to go, then go. Well. Yeah, you should have a periodic table just to kind of like know how to solve this.
Isn't it amazing how I have no clue how to answer this question?
All right, does everyone have an answer?
By the way, do we have to fill this out, or can we use this as a guide to take notes?
I do. I think I'm going to check it tomorrow. So whether you do it as you do your notes or whether you do it for homework, I want it to be done by tomorrow.
Okay.
Oh wait, you think?
Yeah, that packet that the worksheet that I just gave you. In terms of studying, I think you guys should, I think I said it before, but I think my PowerPoints, make sure you know like every single thing that's on there, right? There aren't that many things on there, right? But just make sure every term or every definition or every relationship that's on there, make sure you know that, right? Make sure you know everything that's on these worksheets too, because usually those worksheets go like step by step and try to lead you into like some sort of conclusion. So they ask like tons of like a lot of questions, but that they kind of build up, right? So it's not like each question is hard in itself, but the concept is sort of like leading you to it, right? So that the PowerPoints, any notes that you take like beyond like that, any like handout that I give you. Again, you guys can use the book. You have books, right? You can use the books to like kind of supplement what we're talking about in class, just to kind of, if you want to see it in words, if you're like more of like a what's the word, literary sort of learner, right? But a lot of the things in the book are something you're not responsible for all of that, so it might just end up confusing you. But try to use a lot of different resources, and if like you still are like, I have no idea what's going on, maybe you just need like practice and you need someone to drill you. So that's what your friends are for. That's what your tutors are for. That's what I could meet you like once a week or something and review some stuff if you want to do that one-on-one, or like in a smaller group. That's fine too. But just reach out before it gets too late. Okay, how many covalent bonds does C want? So what's C, and where is C on the periodic table? George? Which? It's in the fourth group, right? So that means how many valence electrons does it have? 4. That means it has 4, and how many does it want? 4 more. It wants 4 more, right? 1, 2, 3, 4. So how many covalent bonds is it going to make?
4.
It's going to make 4, right? What about, so whenever we see a carbon anywhere, what do we want to see around it? 4 covalent bonds. It could be this. It could be something like this, right? Because this is 2, 3, 4. Or it could be what? Something like this, like 1, 2, 3, 4. It can't make a quadruple bond with something else. That doesn't work. But it could be like this and then that. Yeah, so this is a triple bond, and then there would be something else, like, I don't know, like, let's say another carbon there, right? But they would each have to have 4 around it, right? This one has 4 around it, this one has 4 around it, right? All right, what about hydrogen? Which group is hydrogen in, Jasmine? It's in the first group, which means it has how many valence electrons? 1, and how many does it want? A lot of you guys wrote 7.
2.
Why does it not want 7? Because how many can fit in that first orbital?
2.
Just 2, right? So it only wants 1 extra, so how many bonds will it make? 1. So whenever you see hydrogen, you always want to just see like that. It's as simple as that, right? Hydrogen can only have 1 of those like lines coming out of it. What about oxygen? Oxygen has how many valence electrons? 6. 1, 2, 3, 4, 5, 6, right? How many does it want?
2.
2 more, right? So how many bonds will oxygen form with other things?
2.
So oxygen oxygen could look like that, right? Or oxygen could look like that. Would I do this on the other side of it? No, because then how many does it have? 3. So that doesn't work, right? So it can either look like this, or it can look like that, right? So it can have 2 things on it or that. We're good? Okay, yes?
When you have chains, how can you tell which one is bonded?
Huh?
Like when you have multiple different elements, how do you know which one is bonded?
The lines.
Like if you have CO2.
So if I do this,
So yeah, we just have.
You just, I'm not going to ask you to know that. You'll just know that in chemistry when you learn chemistry. But now you don't have to know that, except the ones that I give you to memorize. Okay? All right, but that's a good question. Okay, so organic molecules. So these are just like some basics about organic molecules that I want you to know. Organic means that usually what do they contain? What's the main element that like makes them organic molecules? Carbon, right? Good. So they're made of carbon, right? They're also sometimes called macromolecules or biomolecules. Bio because they're the source of, or the basis of life. And macro because what? What does macro mean? Versus micro. Massive, right? So macro means like humongous. So it's not just like one carbon, two carbons, it's like hundreds of carbons, right? Do you guys know what the 4 classes of biomolecules are? And these, we're going to go through them step by step in this course, but the first one we're going to talk about today is carbohydrates, right? What are the other ones? Proteins is one, good. Amino acids are the components of proteins. So proteins, what else? Lipids, good. Lipids are fats, good. And what's the last one? The most important thing that makes you you in life and everything. DNA and RNA, which are both collectively called. Anyone?
THC.
The NA part of DNA stands for what?
Nucleic acids. Oh my god.
Nucleic acids, good. So carbohydrates, lipids, nucleic acids, right? Which is DNA and RNA. And then proteins, right? 4 different types of biomolecules. We're going to go step by step. Today we're going to start with carbohydrates, okay? This is just intro. Good? All right. Next page. Next slide.
Almost.
Okay. Here we go. All right. So let's just break down the word and tell me what 3 elements you think are in carbohydrates. So carbo, Arnav?
So carbon,
Carbon, good.
then hydrogen, and oxygen.
Good. Hydrate, if I say you're dehydrated or you need to hydrate, what does that mean? You need water. So, sorry. So carbon, hydrogen, and oxygen, those are the 3 elements, but they're always in a fixed ratio in carbohydrates. So they're always basically CH2O, which is water, right? That's why they're called carbohydrates. And then there can be any given number of these together, right? So this N would apply to the carbon, and it would cause all of this ratio to change. So let me just give you an example. So this N could be 3, 4, 5, or 6, right? Meaning that there would be 3 carbons, 4 carbons, 5 carbons, or 6 carbons, right? So let's say like a carbon, like one with 3 would be like this. This would be like a 3 carbon one, right? N would be 3 there, right? Do you understand?
Mm-hmm.
Yeah? And then one with 4, if I made this N4, then that just means that there would be 4 carbons there, right? Like in a string together. Right? If the N was 5, then it would be what?
Another one.
Pretty makes sense, right? And so for every C that I have, how many H's am I going to have? 2. And how many O's am I going to have for every C that I have? 1. Like it's going to be a 1-to-1 ratio, right? So suppose suppose the N is 3, right? How many carbons am I going to have then? 3. How many hydrogens? 6. And how many oxygens? 3 again, right? Did that answer your question or no? Good? All right. Okay. So basically, so let's suppose I have a 3 one like this, right? And you guys understand why I'm drawing the 4 lines around it? Because that means it's bonded to 4 things each time, right? Mm-hmm. Okay. So suppose I have, what we can do is based on the number of carbons, we can name this whole thing, right? So this thing, what you do is you have a prefix, which indicates the number of carbons, and then you put O's on the end, which means sugar, right? So let's try this, right? So the prefix 3, suppose I have 3 carbons, right? Then, and it's a carbohydrate because it has C, H, and O in this ratio. What would I call this? I would call it a triose. Good? Easy?
I'm
Oh.
so lost.
Okay, so suppose I give you a carbon molecule, right?
Oh wait, I think I got it now.
With 3 carbons,
Oh, and yeah, okay.
and then OHs in the ratio of that.
So quad. Okay, wait, no.
So then it becomes a tri. I say this is the trios, right?
Yeah. With
Okay, so now I give you one that has actually 4 carbons on it.
All right, cool.
The prefix refers to what? The number of
carbons.
carbons.
Oh.
All right, so all right, so we're not using the Latin one, we're using the Greek one. So you use it's called tetros, like a tetrad or like a tetris, yeah? So that means 4. So this is called a tetros, right? Because it has how many? Because it has 4. So this would be a tetros, right? Are you with me?
Yeah. We still know the Greek ones.
Okay, they're similar. All right, what about 5? 5 would make it a what? Pentos, good.
Oh wait.
Okay.
And 2 examples of pentoses that you guys know and love are the 2 sugars that go into DNA and RNA. So ribose and deoxyribose. This is a sugar, but this sugar goes into the nucleic acid. All right? All right, and what about 6? Huh? Hect. You're close. Hexose, right? And hexoses are the ones that we're really going to care about because one of the main hexoses, so hex means how many? 6. So let's plug that into this equation, right? If we have 6 C's, then how many H's are we going to have? 12. And how many O's are we going to have? 6, right? What is that? Glucose, right? So that's why we're going to talk about hexoses the most. And today you're going to build them. So that's going to be good. Okay. So remember the N number refers to the number of carbons, right? And then that molecule itself it's called a monosaccharide. Okay? When did you leave? I didn't even notice it. You left. Okay, thank you. Not to be, not like, oh, I didn't even care, but I just didn't notice. He was very quiet. Okay. All right, so I want to talk about this word functional group, and we're going to talk about this a lot when we talk about molecules. So you just have to kind of like memorize this, okay? So there are 2 different functional groups in carbohydrates, and it's basically like if we have this carbon chain coming along here, right? Remember I left these other ones blank? But basically if I put this, for example, on here, OH, right? That's called a hydroxyl group. So if you ever see this coming off of some chain, you know that that's called a hydroxyl group, right? And it can be depicted like O-H, or sometimes it can just also just be depicted as OH, like that, right? But you know that the O is bonded to that H, right? Or it can also sometimes be depicted as that, right? Because if I'm on this side, I want to show that the oxygen is the one that's connected to this molecule, right? Not the hydrogen, right? Can I do this? Why? Because hydrogen can form how many bonds? Hydrogen.
One.
Hydrogen can only form 1, right? But in this
Whoa,
case,
it's
it's forming with oxygen, so this doesn't work, right? That's why we have to draw it like this, right? To show that oxygen is the one with 2 bonds, right? Okay, so that group, OH, whenever you have OH connected to a molecule, it's called hydroxyl group, okay? So that's one of the functional groups that carbohydrates always have. Do you think that's polar or nonpolar?
That's polar.
Polar, why? Because oxygen is bonded to hydrogen, which is very non-electronegative, so it's going to pull all the electrons, right? Okay, so do you think carbohydrates are going to be soluble in water or not?
No.
Yes.
Ionic bonds are soluble, right? Because they're salts. Wait.
If
so
it's
no.
partially charged, does water like things that are charged or not?
No.
This is the problem with your quiz because a lot of you guys didn't get this right, but you have to know what's the structure of water?
H2O.
Okay, and is it charged or not?
It is.
It's partially charged, right? So will this like thing, suppose I put a positive thing in here.
Yeah, so.
Is it going to like it? Yeah, it's going to go right over to here. What if I put a negatively charged thing in it?
No.
It's going to go right over to this. right?
It's the water launch.
So water loves charged things, whether they're ionic salts, which are completely charged, or whether they're other water molecules which are like partially charged. Water loves things that are charged or polar, right? All right. Don't tell me that it's that. So this is anything. So OH, anything with an OH, is it going to be hydrophilic or hydrophobic? Hydrophilic, because it has that polar OH bond, right? Are we good? Okay. All right. This is one of the functional groups that you'll always recognize. So if I give you a molecule and you notice that the ratio is C, for every C there are two H's and there's one O, and it has hydroxyl groups on it, then you can suspect that it's probably a what? A carbohydrate, okay? There's another functional group that is also always in carbohydrates, and it's called the carbonyl group, right? And this group looks like this. Do you see what's going on there? So carbon is double bonded to oxygen, right? And then there are two other random groups here and here. We don't, not O, sorry. I'm not going to put O, that looks like it's like oxygen, right? There are two other like random groups bonded onto these side, right? But the main thing that makes this a carbonyl is this thing right here, the carbon double bonded to the O. Okay? So if you see a molecule with a carbon double bonded to an O, then and it's a ratio of CH2O and it has hydroxyl groups, what is it definitely? A carbohydrate. Are we good? Okay. There are two different types of carbonyl groups. One is called an aldehyde. Huh? That's kind of like formaldehyde, exactly, right. So it's, do you see so you see this is why it's a carbonyl, right? But what's the difference between these two groups? This one has what here?
Hydrogen.
So one of the groups attached to the carbon is a hydrogen, and the other one is just some random other side chain. So it's usually composed of carbon, so it might be like carbon, 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 whatever. It doesn't matter. R just means like some given carbon chain, right? So one of them is going to be a carbon chain, and one of them is going to be an H. That's for an aldehyde, right? And R just means the remainder group, so that's why it's an R. With me? Not lost. Okay. The other type of carbonyl, and again, this is still a carbonyl, because what will it have in the middle then? It'll have a carbon double bonded to an oxygen, right? But in this case, tell me the difference between this one and this one. Bro?
The first one has one carbon chain and a hydrogen, and the other one has two carbon chains?
Yes. So this is some random carbon chain here. We don't. It doesn't really matter what it is. It's like blah, blah, blah. But this one is also another carbon chain. The reason I put that R, like R versus R prime like this, just means that it could be any two different carbon chains coming off of it, right? But what was the difference? This one always has hydrogen there, right? Whereas this one doesn't have a hydrogen. This one's like right in the middle of two carbon chains, right? Are we good? So if I gave you like a list of different molecules, you'd be able to identify which one's an aldehyde and which one's a ketone, right?
Yeah.
Yeah.
I think without my notes I'll be fine.
Okay.
Alright, this one?
Okay. So basically the way to remember it, the way I remember it, is I think of ald, which sounds kind of like old, right? And when you're old, you're at the end of your life, right? So ald, old, and see how this is at the end of the chain right here? Because one of them is a what? One of them is an H, right? So these are both aldehydes, but they're aldoses. Why are they? What does ose mean again? Sugar, because that means they have what other group? So here's the carbonyl group. What other group do they have that identifies it as a sugar? Hydroxyl group, right? All right, you got it? All right, so the other one is called not aldehyde, but it's called a ketone. So if it's a sugar, it would be called a ketose, right? And that's when it occurs, when the carbonyl group occurs in the middle of a chain, right? So do you see how this is different from that? right? So here's the carbonyl group, right? And what's attached to this middle carbon? One over here is a carbon, right? And one over here is a carbon, right? Is there a hydrogen connected to the carbon of the carbonyl group? No. So that's why this is a ketose, right? Do you see the same thing here? This one's in the middle, and what are the two things attached besides the oxygen? This one is a carbon, and this one is a... In this case, what are the two things attached to the carbonyl carbon? This one is a carbon, but that one is a hydrogen, right? Okay. Tell me what the R groups are. Where are the R groups in this case?
The R groups is right above like those four, and then like below is like the 10 elements. Yeah, the 10.
So this is an R group, so we could say this is R, and this could be R prime, right? All right, and what about in this one? Here's R, here's R prime, right? What about in this one? Does this one have R groups?
It has
One, right? And that means it's this, right? And then this one. Okay. You're okay? All right, this is easy. This part is really easy. Okay. So I want you to classify this, and I want you to tell me. Oops, no, don't look. Okay. All right. So Mike. So I want you to tell me what the prefix is going to be for this one. Right. So to determine the prefix, you have to count what?
many carbons.
Good. So how many carbons are here?
3 since the trios.
So it's a triose. Okay. And then now I want you to tell me. Look at the carbonyl group. You see the carbonyl group is highlighted? Right?
Yeah.
Carbonyl
so
means...
the ketose.
Good. Why? Because what's it bonded
It's
to?
in the middle.
It's in the middle because this is a R, right? Because it's a carbon. And this one's also a carbon. So this is ketose. Perfect. Good. Right? This is like... easy. Okay. Let's try this one. All right. Arya, tell me, based on the prefix, like give me the prefix for this one. How do I figure out the prefix? Huh? Okay, you're right, but I want the prefix. So the prefix is determined by the number of carbons, right? How many are there?
6.
So what's the prefix for hexose, right? So this is a hexose, and you also said it's a what? Aldose. Why? Why is it an aldose?
There's the carbon and then the 2 bonds to oxygen.
That makes it a carbonyl, but what makes it an aldose instead of a ketose? You're not looking at this part, but you're looking at that carbon and then what it's bonded to on this side versus this side. This side is what? It's bonded to what? A carbon. So that makes it what? That makes this whole thing what? An R group, right? But what on this side, what is it bonded to? Hydrogen, right? And that makes it because that makes it at the end of the chain. It's not in the middle, it's at the end, so that's called an aldose, right? Okay. Did everyone get that pretty well? All right, here's where it kind of gets crazy, so this is, and you guys are going to have plenty of practice if we get enough time to build these models, right? So what happens is we have this original molecule, right? And all of the ones that we've been talking about so far have been what? They've been kind of linear, right? They've been like linear like this, right? All right, we're good? So that's how we've been classifying whether it's an aldose or a ketose. But in reality, what happens is when we add this thing to water, it forms a ring. So it looks like this. Don't get scared. We're going to talk about this.
Oh no, it already happened.
All right? All right. So I want you guys to look and I want you to recognize it. So this is where the carbonyl group was originally. It just sort of like spread itself out over 2 different carbons, right? But I want you to count how many carbons there are. So let's start over here. How many do we have?
1, 2, 3, 4, 5, 6.
6, right? So it's a hexose, right? Hexose means what? How many carbons?
There are 6 carbons.
Okay, so that means how many hydrogens will there be?
12.
12, and how many oxygens will there be?
It's glucose.
6. So this is glucose in water, okay?
Whoa.
Do you see what happened? It's basically all these carbons still attached to each other. They each still have 4 things attached to themselves, right? But it just makes a ring, all right? in real notation, and this is just a notation. Do you have a question?
Are there? Okay, so we have that, but there aren't any C's.
I'll get to that in 1 second. So, this is just like once you get into organic chemistry, what chemists like to do, they stop drawing the C's, and they'll just draw it like that.
Yes.
So basically, anytime you see a point that has 4 things coming off of it, because they're chemists and they use this stuff all the time, they know that that's what 4 bonds means carbon. So they'll take all the C's like in these parts out and just make them like, and you're supposed to know that the carbon's there. All right? Sometimes what they'll do even is they'll even take out the regular hydrogens, like the normal hydrogens, like this hydrogen, this hydrogen, this hydrogen, this hydrogen. Like they won't take out the OHs because the OHs are needed, but sometimes they'll just take out the hydrogens too. So that makes it fun, right? So what they'll do is, so the diagrams sometimes they're drawn without C's, but you have to know that the C's are there. Sometimes, again, like we said before, they're drawn with HO, right? Do you see that? Instead of OH, because they want to show that the H is going to be on this side, right? This one they just put OH here, but sometimes they'll draw it HO, and that means the same exact thing. Okay? And sometimes, like I said, they'll draw them even without these H's here. Not the OHs, but they'll draw them without the single H's. And that's just to make things more complicated. Okay? Are we okay? No?
No, yeah, it's fine.
You're fine? Okay. We're gonna, no? Not okay?
Yeah.
Lidu?
I'm good.
All right. If you have a question, ask. Like, I don't mind answering questions. Is anyone lost? No? From the beginning? Yeah?
In the ring formation, is there supposed to be a carbon double bonded to oxygen?
No. That's a good question. This oxygen basically came from that carbonyl, but it becomes like, it becomes bonded to 2 different carbons.
Okay.
But yeah, the carbonyl it disappears once it's in the ring formation. Okay. All right, so common monosaccharides, these are the ones that you guys are going to build today, right? So glucose, galactose, and fructose. Huh?
I'm thinking about like alien glucose. Galactose.
All right. So what do we say the formula is for glucose? Shh.
C6H12O6.
Good. The formula for galactose is also C6H12O6.
Whoa, where's the like?
The formula for fructose is also C6H12O6. These are all hexoses, right? And they're all carbohydrates because they all have the same exact ratio. So it's the same formula, right? But are they the same? No, why would they be? If we have different names for them, they wouldn't be the same, right, Mike?
Then how would you tell the difference?
You'll see. And this is what we're going to do. This is what you're going to do today. It's the arrangement of the molecules, right?
Big brain.
So, can I go to the next page?
You made receipts.
All right. So basically, it's just the structure that's different, right? I wanted to get rid of this thing to kind of not confuse you guys. Okay. So I want you guys to just look at this one. Don't look at that. All right? Shh. Galactose looks like this. And you guys have these on your papers, right? And then fructose looks like this, right? So just look at those 3, right? So basically they have the same formula, but they have different structures. So molecules that have the same formula but different structures are called, does anyone know?
Saccharides.
These are all monosaccharides.
We tried.
Close. What are 2 things that have the same number of protons but different number of neutrons?
Isosaccharides.
Isotopes. So these are called isomers.
Mercs. Oh,
Mers.
Isomers. I've heard that before.
Okay, so they have the same formula, different structures. All right? So these are all, what kind of sugars do we say these are?
Hexoses.
Hexoses, right? And each one, because it's just one single molecule, it's one single molecule, this is a monosaccharide. This is a monosaccharide, this is a monosaccharide, right? Today we're going to build these monosaccharides with our kits. all right, with our model kits. And hopefully by the end of that, you'll sort of see how they go together better. Okay, George?
Why is fructose considered a hexose, but it's a hexagon?
1, 2. So remember, these points are all the 6, right? Do you see that other one right down there?
I do.
Yeah. So that's why it makes a 5-membered ring here. These are all 6-membered rings, but it has that extra carbon here and here. So it's still 6 in a row.
Is there a certain reason why the bottom 3 lines are more bolded than the top?
It's just to kind of show that it's like this ring. It's like a perspective. It's like you're supposed to be kind of looking at the ring like back into the, But there's nothing, you don't have to do that.
I don't like this.
Okay. All right. DNA and RNA are made of these 2 sugars called ribose and deoxyribose, okay?
Oh, it's like deep. Wait.
All right, listen. All right, so how many carbons are there here? Let's count them.
1, 2, 3, 4,
5. So that makes this a what? A pentose? So what should the formula be? C?
10, 05. Let's go.
Okay, so and it has, how many oxygens we have? 1, 2, 3, 4, 5. We're good, right? But then deoxyribose, what's the difference between these 2 things? There's only one difference. Omar?
There's one less atom of oxygen.
Yeah, instead of an OH here, this is an H, right? So the formula for deoxyribose would be what? It's still a pentose, so it's still C5.
C5,
Still have H12,
O4.
but instead it's going to be O4.
What
The
is
H10.
It still has 12 H's, so it's the same exact formula, except... Sorry. Is that what you were... Alright. Is that right?
Yeah.
So we have C5H10O4, right? So, are these isomers of each other? Why?
They have a different.
Because they have different formulas. They have similar structures, but they have different formulas, so these are not isomers. But the isomers that we did learn were glucose, galactose, and fructose, right? George?
Why? So for the deoxyribose one, like in the top left, it says CH2OH, like all in the same strand.
So that's another way to kind of so that's another, I'm glad you asked, because that's like a shortcut notation. So it's like if I did this, right, here's my oxygen, I'm just going to draw it all out. So you see how this is like, so here's the H coming down here, and then from this carbon here is coming in a C, an H here, and then an O, and then an H. That's basically what it's saying. So it's saying CH2 and then OH, right? And when you guys build the models, you're going to build it all out like this. So you'll get a better feel for it once you start doing the models, all right? Okay, so are we okay, Sora?
Yes.
No? All right. So, okay, so what kind, we did this. What kind of carbohydrates are these 2? Pentoses, right? Good. What's the formula? We did that. So C5H10O5 and then C5H10O4. Are they isomers?
No.
No. Okay. So I want you guys to come over here and look at these kits, all right? You guys should all have like a model in the back of your, so, can I borrow yours or something?